Welcome back. The inverter in this room, that machine broke down, so this delay. Anyway, so in the last video I got confused in the proof of this theorem, so let's go through it once more. So here again excuse me, we are given three fields L, K and F. It is given that L is an algebraic extension of K and K is an algebraic extension of F. We need to prove that L is an algebraic extension of F. That means we have to prove that every element in L is algebraic over F. So let us start by choosing any element in L. Let U belonging to L be any element. So since it's given that L is algebraic is an algebraic extension of K, so U will be an algebraic element in L over K. So that means U will satisfy a non-zero polynomial over K, and we have already seen that when that happens, such a polynomial can be chosen to be a monic polynomial. So since U is algebraic over K, there exists a polynomial which looks like this. In the polynomial ring Kx, such that U satisfies this polynomial. That means if you replace x with U, you will get 0. Okay, now we are going to consider the extension this extension. The extension obtained by adjoining these elements sigma 1, sigma 2, etc. to F. And then the confusion started. The proof says this: since K is algebraic over F, several applications of Theorem 513 implies L is a finite, M is a finite extension of F. Exactly how are we applying this theorems several times to conclude that this is a finite extension of F? So that's where I got confused. And the thing is this. So first of all, since let us again see what we have written here. Since K is algebraic over F, so every element in K. what I have written here is not exactly, I mean the way I have written here is wrong. Is an algebraic, see again and again I am making this mistake. Is an algebraic extension of F comma several F and then whatever we have written. Okay, so because K is an algebraic extension of F, so all these sigma i's are algebraic over F. So to start the process, it means what? If we adjoin sigma 1 to F, then this theorem says that this is a finite extension of F. This degree is finite. Okay. Now then we again apply theorem 513 and conclude that this is a finite extension of this, this field F sigma 1. Because this is after all an extension of F sigma 1, we are bringing something new into F sigma 1, adjoining sigma 2 to F sigma 1. So this is an extension of F sigma 1 and we are saying that this is a finite extension of F sigma 1. The question is how? And the answer is this. See, because sigma 2 is algebraic over F, so sigma 2 satisfies a non-zero polynomial of some degree over F. Okay, and say that polynomial is hx. Okay, so that h sigma 2 is equal to 0. Now then of course a polynomial which again is satisfied by sigma 2 but that is also of smallest possible degree will be there, and the degree of that polynomial is known as the degree of sigma 2 over F. We already know these things. But now because F is contained in F sigma 1, so this polynomial hx can also be considered as a polynomial over F sigma 1. And so sigma 2 is satisfying a polynomial over F, which also can be considered as a polynomial over F sigma 1. So that means sigma 2 is satisfying a non-zero polynomial over F sigma 1. So sigma 2 is algebraic over F sigma 1 also, and that is why this extension is a finite extension of F sigma 1, and hence this degree is finite. Okay, and because these two degrees are finite, by theorem 511, our first result, this thing will be finite. This thing will be finite because by theorem 511, this is the product of these two things, these two integers. Times this. So that's how we get the conclusion that this is a finite extension of F, and this extension is written as sigma 1 comma sigma 2. Now you repeat the procedure and you ultimately get the fact that M is a finite extension of F. Okay, here we are getting that in the second step the extension that we are getting is a finite extension of F. So after n steps also you will get a finite extension of F. So that is the reason, and that's where I got confused. So now the rest of the proof is just as before, we have already seen, but still again let us complete it. So that means M is a finite extension of F. Okay, since U satisfies a polynomial whose coefficients are in M, because U is satisfying this polynomial, this one. So its coefficients are 1, sigma 1, sigma 2, etc. up to sigma n, and clearly all of these things are in this extension M. So that means U is algebraic over M. Satisfies, we should perhaps write here a non-zero polynomial, or the non-zeroness will follow from the fact that the polynomial being satisfied here by U is actually a monic polynomial. Okay, so either you can write non-zero or you can write monic. So U is algebraic over M. So by theorem 512, MU is a finite extension. Naturally, if an element is algebraic over some if an element is algebraic over some field, then you adjoin that element to the field, you get an extension that will be a finite extension of the original field. That's what theorem 512 says, and the converse is also true. If the extension is finite, then the element that has been used to extend the field, that will be algebraic over the field. So this is a finite extension of M. Now by our first result, theorem 511, MU is a finite extension of F. MU is a finite extension of M, that we have concluded here, and here we have concluded that M is a finite extension of F. So MU is a finite extension of M and M is a finite extension of F. So our first result says that MU is a finite extension of F. And in fact, the degree of MU over F is equal to the degree of MU over over M times the degree of m over f. But then by theorem 512 again, U is algebraic over F. Okay, before we proceed, let us be absolutely sure that we have actually proved the result. What have we concluded here? Mu is a finite extension of F. Okay, and from that we are saying that U is algebraic over F, and we are simply saying that theorem 512 is implying this thing. Is it really that straightforward? Theorem 512 says this: K is an extension of F and A is an element in K. Then A is algebraic over F if and only if A is a finite extension of F. What are we having here? Mu is a finite extension of F. And we are saying that this implies U is algebraic over F. It's not exactly matching, do you see? We have FA and F here, but here we have F, but here we have M. So that means you don't directly get this conclusion. There is an intermediate step. If you think about it a little, the intermediate step becomes clear. You see, M contains F. Why? Because M is, after all, an extension of F, precisely this extension. Okay, so Mu contains Fu, right? And of course Fu contains F. Now the statement that Mu is a finite extension of F means what actually? It means that as a vector space over F, Mu is finite dimensional. Now these inclusions tell us that Fu is a subspace of Mu as a vector space over F. So because the dimension of Mu over F is finite, so automatically the dimension of the subspace Fu over F will also be finite, because subspaces have either equal dimension or lesser dimension than the original space. So this statement actually implies Fu is a finite extension of F, and the reason is this: Fu is a subspace of Mu over F, and then theorem 512 now implies, now you see, now you have Fu, not Mu, that U is algebraic over F. So that's what we want, and that is our final conclusion. So now everything is okay, there is no confusion. So the proof ends here, but this intermediate step, a little thing is there which one should not overlook. Okay, now after this there is that notion of an algebraic number that we were talking about, we mentioned in the last video. So let us properly define it now. A complex number is said to be an algebraic number if it is algebraic over the field of rational numbers. Since the field of rational numbers is a subfield of the field of complex numbers, so this definition makes sense. You can consider any complex number. It may or may not be algebraic over the field of rational numbers. If it is, then it's called an algebraic number. And then after this there are some words, some more words from the author, and then we will turn to the exercises. So let us see what he has to say. A complex number that is not algebraic not an algebraic number since the words algebraic number it's a noun, no. So when we say a complex number is algebraic without mentioning, if we use the word algebraic as adjective, it is adjective without saying anything more over which field, then you have to assume that it's over the field of rational numbers. So a complex number that is not an algebraic number is called, they also have a name, is called a transcendental number. At the present stage, but before we say something about transcendental numbers, let us quickly see some actual concrete algebraic numbers. Trivially, every rational number is an algebraic number, because rational numbers are after all also complex numbers, although they are real but still complex numbers. So all rational numbers are automatically algebraic numbers. Why? If you take any rational, let me just grab this place. Say you take a rational number, since we are saying concrete, let us take 2, which actually is an integer. It satisfies this polynomial. You take any other rational number, say -1/2, then this satisfies the polynomial over Q. In general, you take a rational number R, it satisfies the polynomial x minus R. Because R is rational, x minus R is actually a polynomial over Q. So every rational number is an algebraic number which is algebraic over the field of rational numbers and is of degree 1, because this is the minimal polynomial. There are of course irrational numbers also that are algebraic. For example, square root of 2. It is a complex number that is not rational, but it satisfies this polynomial over Q. These examples are easy. More complicated examples are coming in the exercises. But this definition that a complex number that is not algebraic is called a transcendental number does not by itself give us any reason to believe that transcendental numbers actually exist. So that's what we are saying. At the present stage, there is no reason to believe that transcendental numbers exist at all. In the next section, we are going to show that they do exist. We will show that the familiar real number E, which we have come across in analysis, is a transcendental number. If you are wondering about these examples, if you are wondering about whether there are algebraic numbers that are not real numbers, yes, there are. I itself is an algebraic number because it satisfies the polynomial x square plus 1, which is a polynomial with rational coefficients. Like this, you can find that many algebraic numbers are there which are not necessarily real numbers. Okay, so let us continue what we were writing. That the familiar real number E is transcendental. This of course tells us that transcendental numbers exist, establish the existence of transcendental numbers in fact transcendental numbers exist in great abundance. Let me put some ink first. In a very well defined way, there are more of them, more transcendental numbers than there are algebraic numbers. Then Theorem 514 which says that all the elements in K which are algebraic over F form a subfield of K. That has application here. I mean, in this particular case, that theorem says that all the algebraic numbers form a subfield of the field of complex numbers. Applied to algebraic numbers proves the interesting fact that they form a subfield of the field of complex numbers. That is sums differences products and quotients when they can be formed of algebraic numbers are again algebraic numbers. Which of course is a non-trivial fact. It's not at all clear why a plus b should be algebraic if a and b are algebraic numbers. And this field of algebraic numbers is less, because of that reason, is less obvious than the other subfields of C with which we are more familiar, like the field of real numbers or the field of rational numbers. Besides this, Theorem 515 when used in conjunction with the so-called fundamental theorem of algebra. Has the implication that the roots of a polynomial whose coefficients are algebraic numbers are themselves algebraic numbers. This one I leave to you to figure out exactly how this is true. That is, if you take any polynomial where the coefficients are algebraic numbers, then all of its roots are also going to be algebraic numbers, and this follows from Theorem 515. I believe it is Theorem 515, but I think I also somehow thought of a way in which Theorem 514 concludes the same thing much more easily. So I leave it to you to figure out. One more thing is, what is the fundamental theorem of algebra? You can of course look up, but since we are discussing these things, let me tell you. The fundamental theorem of algebra says that any polynomial over the field of complex numbers has at least one root which is a complex number. That is the fundamental theorem of algebra. If you mix this with how one can, for example, what I am trying to say here is this. Say the fundamental theorem of algebra says that such a polynomial has a complex root. Say that root is a. Then you can write fx as x minus a times another complex polynomial f1x, where the degree of f1x, clearly from this equation you can see that the degree of f1x is 1 less than the degree of fx. Then you apply the fundamental theorem of algebra on f1x. It can also be written as x minus one of its root times another complex polynomial. This way you can completely factorize fx as a product of linear polynomials over C. Okay, so that thing you have, and you have these two theorems. From that, somehow you have to conclude that these roots are actually going to be algebraic numbers if the coefficients here of fx are not arbitrary complex numbers but themselves are algebraic numbers. Okay, so here this section ends, and we are now going to go to the exercises. So let's do that. The first few are of course routine things, things that we left unproved in the proofs that we have gone through. So we are going to first complete them, and then we will go to some exercises which one can say numerical, in the sense that we will be given, say, some complex number. We will be asked to find the degree of that complex number as an algebraic element over, say, the field of rational numbers, things like that. So let us start with the first one. Prove that the mapping we have seen this mapping in the proof of 1/2 of theorem 5.1.2, defined by hx psi equal to h of a is a homomorphism. Okay, so we directly take two elements and then try to show that psi respects addition and multiplication. So let hx equal to, so we have to consider polynomials over f. Aix to the power I varies from say 0 to m, 0 to n here I have taken. Anything you can take, it does not matter. And gx is another polynomial which may or may not be this one. Zero to m. N and m are non-negative integers. Let this be two elements in fx. M and n are of course not necessarily equal, but in any case one of them will be less than or equal to the other. So for definiteness, we assume n to be less than or equal to n. Note that in that case hx can also be written like this: summation I varying from 0 to m cix to the power I, where Ci is nothing but ai if I lies between 0 and n, and it is taken to be 0 if I lies in this range. So we have just simply rewritten this polynomial hx by adding some possible zero terms. Say in place of hx, suppose you have this polynomial x plus x cube. Say this is our hx, and gx is the 1 minus x square plus x to the power 4. Then rewriting hx like this just simply means we are rewriting hx like this by adding extra zero terms if necessary, so that this highest degree term that is available in gx also is there. I mean, it's of course there, but with a zero coefficient. So we are just simply making the variation of this I, this indices, the same from 0 to m, so that while adding these polynomials we don't have to deal with this discrepancy between n and m. Okay, then hx plus gx psi, it will be equal to what? Now the sum will be very easy because I varies from 0 to m in both the polynomials. So it will be summation ci plus bi x to the power I, where I varies from 0 to m. On this we are applying psi. I should have written psi on that side, but there is no space. So we are evaluating this polynomial. Applying psi on this polynomial means what? We are evaluating this polynomial at the point A. Okay, so 0 to m ci plus bi a to the power I. Now, using the fact that Fa is a field, all its field axioms, we can write this as a sum of two elements, ci a to the power I, as I varies from 0 to m, and bi a to the power I. So this is nothing but psi applied on hx and this one is psi applied on gx. So psi respects addition between these two rings. Next, we'll look at the product of h and g. This is equal to, for this I need some space. Since here we are dealing with the product of two polynomials, so there is no need to make n and m same. They are not same, I mean there is no need to consider two such expressions having same variation for the indices. So here we can simply write ai, okay, yes, of course, ai x to the power I, where I varies from 0 to n, times summation bi, but because it is product, so let us write bj, because ai and bj are going to be multiplied. Writing a new name for the index. This is equal to, I have space here so I can write summation k varying from 0 to n plus m. Recall the product of two polynomials in a polynomial ring. Summation I plus j equal to k ai bj x to the power k psi. This is equal to so we are going to now evaluate this polynomial at a by the definition of psi. So this will be equal to ai bj, the sum varies over all the terms where I plus j is equal to k, a to the power k, and again using all the rules in the field fa, this becomes equal to the product of these two expressions. I believe the first one was n, yes, bj a to the power j, where j varies from 0 to m, and this is equal to ha ga, which is hx psi gx psi. So psi respects both addition and multiplication, hence psi is a homomorphism. So this completes the solution. Next, exercise 2. Let f be a field and fx be the ring of polynomials. Okay, what is the need to say that again? We already know it, no? Fx be the ring of, I think there is a part, I should not laugh, there is a purpose in repeating these things again and again. It helps us memorize the things much more easily if we say it again and, I mean, at least for the beginners who are looking at these things for the first time. So it may not be the case that when someone looks at fx, then he or she may recognize this as the ring of polynomials. The person may forget also, no? So there is a purpose. Yeah, I get it. Be the ring of polynomials in x over f. Let gx of degree n, it's a polynomial, but over what? Over f, be in fx and, oh, so we are going to look at that thing, and let phi be the ideal generated by this polynomial gx. I don't know why I wrote px, maybe it's coming from that proof that we did. Be the ideal generated by gx in fx. Okay, prove that this quotient, it is fx by phi, this quotient ring is an n-dimensional vector space over f. I have a solution here, but now I am noticing that the solution is incomplete. Incomplete in the sense that in this solution that I have written here, I have assumed that this is a vector space over f. That is the first thing, and I have just shown that the dimension is n. Now recall that in the proof of theorem 512 we came across this, because in that proof we came across this function also psi, and this v which we are writing here, there the polynomial was px, I think I can remember that, and phi turned out to be the kernel of that homomorphism psi. We also proved, because of the nature of px as the minimal polynomial for that element a that we chose in k, if you are remembering the things, because of that minimality, this ideal turned out to be a maximal ideal in fx, because the polynomial we proved was irreducible px. From that, it followed that this quotient ring is actually a field. Now because this field contains F, so F is a subfield of this. I mean, in that case where we did the proof of theorem 5.1, I am talking about that, not here in this general case. So automatically this was a vector space over F because this was an extension over F, but here it's not given that Gx has a minimum degree satisfying that condition. So I think we have to first of all show that this actually is a vector space over F, and then we have to prove that its dimension is n. I have to change this solution. So let us first show that this is a vector space over F. Is that not coming directly from something? Let me once again think. Fx by v no, I don't think that is directly coming from anything. We have to show it from scratch. Okay, so let us start by considering the fact that since this is a ring, after all it's a quotient ring, so that means it's a ring, so it is an abelian group under an addition that it already has. Since this is a ring, I believe we have to show that this is a vector space. If I am missing something, if this the fact that this is a vector space over F already follows from something we know quite easily, which I am not getting at this point, then please let me know in the comment section that yes, it automatically follows from here that this is a vector space over F. Now proceed to show that its dimension is n. If that is the case, please let me know. At present I can't see anything like that. Okay, so since this is a ring, this is an abelian group under the ring addition. That is the addition we have in the ring structure. By ring addition we mean that. Okay. Now we have to define that multiplication by scalar for alpha belonging to F and an element in this abelian group. It will be what? It will be a coset of V in Fx. Where clearly you have to understand that this Fx is coming from Fx. We define equal to alpha Fx plus V. Let us first see the meaning of this. Fx is a polynomial over F, alpha is an element in F, so we are just simply multiplying this polynomial by alpha, where actually what we are doing, since alpha is a field element, it's also a polynomial over F, a constant polynomial. So here we are multiplying two polynomials over F, one of them is a constant polynomial. So the product that we have here is multiplication of two polynomials actually. So that again gives us a polynomial in Fx. So this clearly is a again a coset of V in capital Fx. So the result that we have here is in fact in this quotient tree. Now next we have to of course show that this is well defined. This is a well defined operation. So for that, let alpha and beta be two elements in F and Fx and Gx be two polynomials over F such that alpha is equal to beta and Fx plus V is equal to, we already have Gx here, so we cannot take Gx here. Instead, let us take F1x and F2x. Okay, then F1x minus F2x belongs to V, and because V is the principal ideal generated by Gx, so this difference is a multiple of Gx in the polynomial ring Fx, which implies F1x minus F2x is Hx times Gx for some polynomial Hx in Fx. This implies, now if we multiply on both sides by alpha, then we get alpha F1x minus alpha F2x is equal to alpha Hx Gx. Because alpha Hx is again in Fx, so this is a multiple of Gx again in Fx. So this belongs to phi. Thus alpha times F1x plus V is equal to alpha F1x plus V. The conclusion we draw from this this relation is that alpha F1x plus V is equal to alpha F2x plus V. Alpha F2x plus V, which is nothing but alpha times F2x plus V, and that is equal to beta times, because alpha and beta are the same thing, same scalar. So the operation we have defined here is actually well defined. So the operation we defined above is well defined. Okay. So we now have an abelian group structure on this set, and we have an operation, external operation, where one element from this set is being multiplied by a field element. So we are only required to show that the other 4 axioms are now true. So next, let alpha 1 and alpha 2 be 2 field elements and this be 2 elements from the abelian group. Note that the first thing we note is this: alpha 1 times f1x plus v plus f2x plus v is equal to alpha 1. First we apply addition, the definition of addition in this string, so we get f1x plus f2x plus v. Then we apply the definition of this operation, that gives us alpha 1 times f1x plus f2x plus v. Okay, and that becomes equal to, now since alpha 1 is a polynomial and these are also polynomials, so in the polynomial ring fx, only fx, okay, not fx by v, in only fx, we can apply the left distributive law and write that thing equal to alpha 1 times f1x plus alpha 1 times f2x plus v. Then this becomes equal to, again by the definition of addition here in the quotient ring, plus alpha 1 times f2x plus v. Then by the definition of the operation we defined, we get this. So one of the 4 axioms we need to verify has been verified. Then alpha 1 plus alpha 2 times f1x plus v. By the definition of the multiplication we defined, this is equal to alpha 1 plus alpha 2 times f1x plus v. Now this time, just like we applied the left distributive law here, this time we are going to apply the right distributive law, because alpha 1 and alpha 2 are 2 constant polynomials, after all polynomials. So doing that, we get alpha 1 times f1x plus alpha 2 times f1x plus v, and proceeding like above, we then get plus and this becomes equal to so the second axiom also has been verified. Then the third one, alpha 1 alpha 2 times f1x plus phi. The law we are going to apply here now is just the fact that multiplication in the polynomial ring fx is associative, just like any ring. So we can write this product as alpha 1 times alpha 2 f1x plus p. Now we apply the definition of the operation we defined in this solution 2 times. So this is equal to, first of all, this is alpha 1 times alpha 2 f1x plus phi, and that becomes equal to alpha 1 times alpha 2 times f1x plus phi. So the third one also has been verified, and finally this 1 times f1x plus phi is equal to this, which is just f1x, because this is the constant polynomial 1, which is the unit element in the polynomial ring fx. So that's it. Hence this is a vector space over F. Now we will proceed to show that the dimension is n. Now consider the elements one plus v, x plus v, x square plus v, etc. up to x to the power n minus 1 plus v. All of these are elements in our vector space. We claim that they form a basis for this space, and then once we prove that, then looking at the fact that there are n symbols in number, this will imply that the dimension is n. It's an n-dimensional space over F. So let alpha naught alpha 1, we have already assumed alpha 1 here, but that part is over, so we can use alpha 1 alpha 2 once again. They are after all scalars. In a given solution, once you involve some symbols, once you define some symbols, use them in the solution, whatever you are going to prove, if that has been proved and if the goal has been reached, then you can then again use those same symbols to do something else, because whatever has happened and is over is just over. Okay, this alpha 1, you should not confuse this alpha 1 with that alpha 1, although no problem will appear here, but I am just simply saying, if the original solution has parts which require separate proofs, then the symbols can be used again and again. That's what I am saying. So anyway, so let this be scalars such that this linear combination is 0. So now we want to prove that these elements are linearly independent. Equal to, you have to write 0, but 0 where? 0 in this vector space. In this vector space, the 0 element is the set V. Because don't forget that we are in a quotient ring. So the ideal itself is the 0 vector. I mean the 0 element, which of course in our vector space is also the 0 vector. Okay. Then alpha naught plus alpha 1x plus alpha 2x square, etc. up to this plus V is equal to V. Which implies the polynomial is in V. Now recalling what V is the principal ideal generated by that polynomial Gx. We get the fact that this polynomial is a multiple of Gx. Hence, this is equal to some hx times gx for some hx belonging to fx. Okay. Now from this we have to somehow show that all the alpha i's are 0. If we suppose that alpha I, in fact let's just write like this, suppose all the alpha i's are not 0, then the left hand side is a non-zero polynomial simply because of our supposition. Correspondingly, the right hand side is also a non-zero polynomial. Then hx gx is not equal to 0, and hence hx and gx are individually non-zero. Do you remember why? That is because our polynomial ring is over a field and fx is an integral domain. We have already proved that way back in our videos on polynomial rings. So if a product of two polynomials is non-zero, then they have to be non-zero polynomials, each one of them. But then degree of this product is, from the degree formula, sum of their degrees, which is greater than or equal to n. In fact, let's just write, you may get confused where n is coming from, is greater than or equal to degree of gx, because hx is a non-zero polynomial, so its degree is a non-negative integer. So if we don't write that, we are possibly writing less. So this, which is equal to n, whereas the polynomial we have on the left side, its degree is less than or equal to n minus 1. We don't really know whether alpha n minus 1 itself is non-zero. This may be 0, but there is at least one alpha I according to our supposition that is not 0. So that means this polynomial is a non-zero polynomial and it has some degree, but that degree from how the polynomial looks must be less than or equal to n minus 1, and that is a contradiction, because the right hand side is a polynomial of degree at least n, whereas the left hand side is a polynomial of degree at most n minus 1. This cannot be. Whereas this is a contradiction, and proves that the above supposition is wrong. That is, alpha I must be 0 for all I varying from 0 to n minus 1. This shows that these elements x plus v, x square plus v, etc. are linearly independent. Are linearly independent over F. Whenever you write linear dependence or independence of vectors, please also mention the underlying field, because that matters. That we will see in the chapter on vector spaces. For example, let us just digress for a moment, for a little bit, and see this. The field of complex numbers is a vector space over the field of real numbers, but the field of complex numbers is also a vector space over itself, the field of complex numbers. Now, in this vector space, the complex numbers 1 and I are linearly independent, whereas they are linearly dependent in this vector space. That is, when we are considering the complex numbers 1 and I, over R they are linearly independent, but over C they are linearly dependent. The reason for their linear independence over R is this. If you take the linear combination of 1 and I over R, that means you are considering two real numbers A and B and forming the linear combination. Then it becomes the complex number A plus BI. Now this will be 0 if and only if both A and B are 0. That comes directly from the definition of equality of two complex numbers. So you see that the scalars must be 0. So over R1 and I are linearly independent, but over C they are dependent, because simply because you are now allowed to choose complex number scalars. So you can choose this 1 times 1 plus I times I, that is equal to 0, where none of the coefficients is actually equal to 0. And now because our field is the field of complex numbers itself, so we are able to choose 1 and I. So that's why it matters that we write linearly independent over F. Okay, so that over thing, the underlying field matters. Okay, next we have to show that these vectors, besides being linearly independent over F, they also span the space. So for that, let us take any arbitrary element in the space. Now let fx plus v belong to our space, where of course fx belongs to the polynomial ring. Now what we do, we are now going to divide fx by that polynomial gx to get a quotient polynomial and a remainder polynomial, because we know that the polynomial ring is a Euclidean ring. So in that the division algorithm, the version of the ordinary division algorithm or Euclidean algorithm is available. But before that, let me just see one more thing. Oh, because it is given that our polynomial gx has a degree, so gx is not the zero polynomial. So yes, we can apply the division algorithm, because gx being a non-zero polynomial can in fact divide. It can be the divisor. Okay. By the Euclidean algorithm, if you choose to not write these things, then also it's okay. It's understood what we are doing. By the Euclidean algorithm, there exists polynomials qx and rx again in fx such that fx is equal to qx times gx plus rx. Where either Rx is equal to 0, or if it is a non-zero polynomial, then the degree of Rx is strictly less than the degree of Gx, which is given to be n. Okay. So that means either Rx is a zero polynomial or Rx is a polynomial whose degree is at most n minus 1. Thus, Rx will look like this. For some scalars, we can now use this fact. Now, fx plus v, this coset is qx times gx plus rx plus v, and this becomes qx. If you apply all the operations that we have, okay, let me just first write and then I will say what I have done here. Will it be okay? Instead of writing it like this, I mean, we don't have to go that far. We can just simply write qx gx plus v plus rx plus v. Here we have just applied the definition of addition in this quotient ring, that's all. Now qx gx is a multiple of gx in fx. So by the definition of v, qx gx belongs to v. So this coset is actually equal to v. But in this quotient ring, v is the zero element with respect to addition. So this is equal to Rx plus v. And now you use the expression for Rx. And now if we use the vector addition, which actually is nothing but the ring addition and the multiplication by scalar that we have defined in this solution towards the beginning of this solution, if we use all those things, then this coset becomes equal to this. So you see that these elements actually span the entire space, because any arbitrary element in our space can be written as a linear combination of these elements. So they span fx by v. Okay, let me continue from that side. No need to clutter. We have thus shown that this set is a basis of this vector space over F. So dimension over F of this space is equal to n, and that completes the solution. It's an n-dimensional vector space over F. Let us see another one. Another one I am saying because we have we have lost a lot of time. I should not say lost, but we have utilized most of our time in this solution, because I did not know that the one I had is incomplete, in that sense that I forgot to show that this is first of all a vector space over F. Anyway, so let us see the third one. If V is a finite dimensional vector space, over a field K, and K is a finite extension of another field F. That's not exactly how the question has been written, but it has the same meaning. And if F is a subfield of K, such that the degree of K over F is finite, show that V is a finite dimensional vector space over F, and moreover that the dimension of V over F is equal to the dimension of V over K times the degree of K over F. And in part B, show that Theorem 511, our first result in this chapter, show that is a special case of the result of part A. Here the solution is very small. It's because we are just going to mention something, but now, given that the previous solution was incomplete, this one is also a little incomplete in the exact same manner, which however now you can complete that you have seen the previous solution. Let me first write the solution and then we will see how it is incomplete. If in Theorem 511 we consider L to be a finite dimensional vector space over K instead of a finite extension of K, then the proof that we have in the text, that same proof works. Then the same proof goes through. That means what we are saying is that the proof that we have of Theorem 511, if in place of L to be a finite extension of K, if there you have a vector space L which is finite dimensional over K, then the same proof goes through, but the incompleteness is this. In this case you have to show, just like before, that L is but it is given that L is a, okay, yeah, now I get it. I was thinking that because just like before we are transitioning from a field to a general vector space, so we have to show that it's a vector space, but no, the fact that it's a vector space over K is a part of the hypothesis. So yes, there is nothing else to be done here. You just do one thing, you see that whatever we have written here is true. You go through the proof of Theorem 511 thinking of L as a finite dimensional vector space over K instead of just as a finite extension of K, and you will see that the same proof works. And part B is obvious, because once you have this proof, then the case where L is a finite extension of K is only a special case, because every finite extension of a field is after all a finite dimensional vector space over the field. So here the solution ends like this. Then can we do one more? Let us solve one more exercise so that we can see those computational things that I was talking about. Exercise 4. It also has parts. A. Let R be the field of real numbers and Q be the field of rational numbers. In R, square root of 2 and square root of 3 are both algebraic. Over Q. The reason is quite simple. The first one satisfies this polynomial and the second one satisfies this polynomial, and both the polynomials are polynomials with rational coefficients. That's why. Exhibit a polynomial of degree 4 over Q satisfied by square root of 2 plus square root of 3. So in the proof of theorem 514, which states that the elements in K which are algebraic over F, they form a subfield of K containing F. In that theorem, or its consequence, that the algebraic numbers form a subfield of the field of complex numbers. In that proof, we have already seen that, see, this is algebraic, this is also algebraic, so their sum is algebraic. But the sum is algebraic of degree at most that number which is the product of the degrees of these two numbers. In fact, if you think of it a little bit, because these polynomials over Q are satisfied by root 2 and root 3 respectively, so each one of them has degree at most 2. But at the same time, they can not satisfy linear polynomials over Q. And the linear polynomials satisfied by them are these. Now, these are not polynomials over Q because neither square root of 2 nor square root of 3 is rational. So that's why degree of root 2 over Q is 2, degree of root 3 over Q is also 2. So from the proof of theorem 514, we know that the degree of root 2 plus root 3 over Q is at most nm, 2 times 2, which is 4. So that's why the exercise asks us to actually exhibit a polynomial of degree 4 that this number will satisfy, and over Q, of course. So that is the first part. Then in second part, we are being asked what is the degree of root 2 plus root 3, what is the actual degree. prove your answer. And part C is quite easy. What is the degree of root 2 times root 3 over Q? Okay, so let us see the solution. The first polynomial of degree 4, which root 2 plus root 3 should satisfy, that I am just going to simply mention. Okay, it's your job to see that what I am writing is actually correct. X to the power 4 minus 10x square plus 1. If you are going to ask me how one can find such a polynomial in the first place, the answer is by a direct search. You already have polynomials which the individual numbers satisfy. You try to multiply them, see whether you get a polynomial over Q. If not, then you try to adjust things. Like that, you will eventually find such a polynomial. There may be some more efficient method. I don't know any such method, at least not at this stage. Okay, now we go to the difficult one. We claim so here you just have to substitute x equal to root 2 plus root 3 there and see if you get 0. We claim that the degree of root 2 plus root 3 over Q is 4, is actually equal to 4. Suppose square root of 3 belongs to the extension obtained by adjoining root 2 to Q. Suppose, then I am going to write root 3 in a particular form in terms of root 2 and coefficients and in terms of rational numbers. That is, I am going to write root 3 equal to a plus root 2 b for some rational numbers a and b. The question is, how are we writing this? How do we know that this is the form of the elements in this extension? To see that, you just recall the general form of the elements in FA, that internal description. You recall that. You recall that we recognized FA as U, where U consists of expressions like this. Where n and m are non-negative integers, all the alpha i's and beta i's are filled elements, and the denominator is non-zero. So that thing, if you apply that thing here, Then what is our a here? A is root 2. Now if you look at the expression like this, say first we look at the numerator. Root 2 is not there in the first term. In the second term, root 2 is there. In the third term, we will have root 2 square. So that gives us 2 alpha 2, which is a rational number. In the third term, we will have root 2 cube. So that will be alpha 3 times 2 root 2. So that again is a product of root 2 and another rational number. So after simplifying this expression, you will have a number of rational numbers, a number of rational terms in this sum, and a number of irrational terms in this sum, where each irrational term has the form some rational number times root 2. So ultimately you will be able to write this such an expression in this form, where alpha is rational, beta is also rational. If you want more definiteness, you can take some specific value of n, say n equal to 3. This expression becomes equal to, let me write it here, alpha naught plus 2 alpha 2 plus alpha 1 plus 2 alpha 3 root 2. Because the first one is alpha naught, the second one of course is alpha 1 root 2, the third one is 2 alpha 2, and the fourth one is 2 alpha 3 root 2. So the eventual form is this. But then you ask, okay, but we have to divide again by such a polynomial expression in root 2. So that means our general element in q root 2 is looking like this. Alpha 1 plus beta root 2 divided by alpha 2 beta 1 root 2 plus divided by alpha 2 plus beta 2 root 2. But then you recall that thing from high school where such an expression was multiplied by its something called rational conjugate, which is alpha 2 minus beta 2 root 2, which is somewhat like complex conjugate, to rationalize the denominator. Once you do that and simplify this portion, it will again come to an expression of this form. So in this extension of q, the general form of an element is a plus root 2b, where a and b are rational numbers. But this much of course will not be written in a solution like this. It is supposed to be understood. Okay. Then what can we do from this? This implies we just square both sides and get 2b square plus 2ab root 2. Since a and b are both non-zero, why? If a is 0, then you get a contradiction. because if a is 0, then b becomes square root of 3 divided by square root of 2, which you can show is not a rational number, whereas b is a rational number. If b is 0, then we get an even more direct contradiction that root 3 is irrational but a is rational. So we are just simply going to write, since a and b are both non-zero, you know why. Okay. So we can write square root of 2 like this. Non-zeroness of a and b allows us to divide by 2ab. But then this is a contradiction, because the left hand side is a rational number, but the right hand side you can clearly see is, the left hand side is an irrational number, but the right hand side is a rational number. This is a contradiction, because root 3 is irrational, but 3 minus a square minus 2b square divided by 2ab is rational. And the reason for this expression to be rational is that both a and b are rational. So our supposition is wrong. That is, root 3 does not belong to this. Okay. Hence, the minimal polynomial of root 3 over q root 2 is x square minus 3. We are saying this is the minimal. We already know that root 3 satisfies this polynomial, and this is a polynomial with rational coefficients. And this is also a polynomial with coefficients in q root 2, because the coefficients being rational numbers are automatically also in this larger field extension of q. But because root 3 itself does not belong to q root 2, so the only linear polynomial that root 3 satisfies, this polynomial, is not a polynomial over q root 2. So that's why this is the minimal polynomial of root 3 over this field. And this implies that the degree of this extension over q root 2 which is nothing but this over q root 2 is equal to 2, because the minimal polynomial of degree 2 is of degree 2, since we already know that the degree of this extension q root 2 over q is 2, because the minimal polynomial of root 2 over q is x square minus 2, because of the same reason, following same arguments, similar arguments. So Theorem 511 implies that the degree of this extension over q is equal to this times this is equal to 2 times 2 equal to 4, because we have found the degree of this extension over q and it is 4. Also, since this contains this, which in turn contains q. Why is that true? You see, this extension of q contains q as well as root 2 as well as root 3, and this is a field. So root 2 plus root 3 also is in this extension. So this is a field which contains q as well as root 2 plus root 3, and this by definition of such extensions is the smallest subfield of q containing both q and root 2 plus root 3. So automatically this one will contain this, and since all of them involve q, so all of them contain q. Okay, so now what is happening? You see, this extension q root 2 comma root 3 is a 4-dimensional vector space over q, and this middle one, this intermediate one, because of these inclusions, is a subspace of this vector space over q, and that is why its dimension, not only will it be less than or equal to 4, but it will in fact have to divide 4. So, the corollary to Theorem 511 implies that the degree of q root 2 plus root 3 over q has to divide the degree of q root 2 comma root 3 over q, which is 4. Hence, this degree is either 1 or 2 or 4. We have to now show that the degree must be equal to 4. So that means we have to show that the degree can neither be 1 nor 2. This, however, instead of continuing, because we have quite a number of things to write, we will stop the video here and we will continue in the next video. Okay, so that will be all in field theory tonight. If you have anything to say regarding these things or any other thing about mathematics, you can write in the comment section below, or you can mail me here. So with this, I sign off for tonight. So until the next video, this is me, Lucifer, from a mathematical room. Have a nice night.